Today we're going to be looking at a specific example from the book, example 8 from page 655, and essentially it's determining the accuracy of an approximation. So we're finding an approximation using a Maclaurin or Taylor polynomial, and then we're finding the error afterwards to determine how accurate our approximation was. And we're specifically going to be looking at this example because this example was a little bit confusing, simply because the authors of the book left out a few of their steps, probably for sake of space. And so sometimes it can be a little bit hard to follow, but if we go through it, it'll be easier to understand, and it'll be easier to understand the process that you would have to go through in the future to solve one of these problems. So we're going to solve this problem. So first of all, we're going to define the problem, because this whole thing is kind of like them answering the problem. So we're going to pretend that, oops, that was bad. We're going to pretend that the box that I'm about to make, the better box, yeah, that still kind of sucks. But we're going to pretend that this box represents the question. So use Taylor's theorem to approximate sine of 0.1 by this third degree polynomial and determine the accuracy of the approximation. So they do give you the polynomial up here, and they tell you it's Maclaurin, but if you were just given this, you'd have to solve it alone. So we're going to solve it alone. We're going to pretend that this is the problem. So again, they don't tell you whether or not your polynomial is going to be Maclaurin or Taylor, because you have a choice to make, whichever one you want to use, but a lot of times one is a lot better than the other, and in this case, Maclaurin would be a lot better to use, and this is for two reasons. Well, actually only one reason, but the second reason is a pro. The first reason is you always want to choose a value to center it around that is very close to the approximation, and it'll be easier if you choose a value that's an integer. So 0.1 is very close to 0. So if we center it around 0, then it will be a good approximation, and it will be Maclaurin series. So that's why you should use Maclaurin in this case. However, if it was 0.9, for example, you should probably use a Taylor's polynomial and center it around c equals 1. And the plus to using this Maclaurin polynomial is Maclaurin's a lot easier to do than Taylor, simply because you don't have to worry about the c value, subtracting the c from the x value all the time. So because c is 0. So now that we know that we're going to use Maclaurin, we're going to go ahead and find the Maclaurin polynomial. So first thing we're going to do is write out f of x, which is sine x. And this is the third degree polynomial, so we're going to go all the way to f triple prime of x. So the derivative of sine x is cosine x. The derivative of cosine x is negative sine x. The derivative of negative sine x is negative cosine x. And we can stop there because, again, this is the third degree polynomial. So the third derivative, we stop there. Now we do f of c. In this case, c is equal to 0, so we're doing f of 0 is equal to sine of 0, which is 0. F prime of 0 is cosine of 0, which is 1. F double prime of 0 is negative sine of 0, which is 0, and f triple prime of 0 is negative cosine of 0, which is negative 1. So there we have our first function and three derivatives. And now we're going to write out the third degree polynomial. So we call it p sub 3x. The sub 3 is always going to be, this space is always going to be filled by the degree. So the third degree, we fill it with the 3. And then it's always going to be the f of c term times 1. So in this case it's 0. So you could write a 0 out, but I'm not going to bother because it's just going to add out to 0. So then you take the first derivative term, so f prime of 0 times x over 1 factorial. So that's just going to be 1 times x. So we can write out an x here. And then the second derivative term would have been f double prime of 0 times x squared over 2 factorial. But in this case, f double prime of 0 is 0. So again, that'll cancel out because 0 times anything is 0. And then the third derivative term is f triple prime of 0 times x cubed over 3 factorial. So in this case, that would be negative 1 times x cubed over 3 factorial. And that is how you get this part. And that's the first step. Now the second step is to actually approximate this value. and you want to approximate 0.1. So all you do is you plug in 0.1 here. So 0.1 minus 0.1 cubed over 3 factorial. And that is what they did right here. So sine of 0.1 is approximately equal to 0.1 minus 0.1 cubed over 3 factorial. This is what we're doing right here. This is exactly what they did. And you get a value of 0.099833. So that's the first answer. The first part of the problem is already solved. And that's what they got right here. Now the second part is where it gets a little bit trickier. So we're going to use Taylor's theorem to approximate the error now. And Taylor's theorem says that the error of the third degree is equal to the n plus 1 derivative of z, where z is any number between x and c that will minimize this number. That will maximize this number. We want to maximize it so that we're more conservative, which means that we want to have more error so that we can be more sure how close we are to the actual value. So we want to maximize this. And we multiply that by x minus c to the n plus 1 term, to the n plus 1 power, all over n plus 1 factorial. That's the formula. Well, this is actually supposed to be an n, but in this case, n is equal to 3. So this is the general formula. R sub n of x is equal to this generally. Now we're going to plug in the 3, because we know that n is equal to 3 in this case. So the fourth derivative of z times, we also know c, so we're going to also put that in there. C is 0, so x to the fourth over 4 factorial. And we know what x is, so we're going to plug that in. And we also know, we're also going to plug in what the fourth derivative of f is. So the third derivative of x, which we calculated up here, was negative cosine of x. So the derivative of negative cosine of x will be the fourth derivative, which is sine. So essentially, we're going to be taking the sine of z times 0.1, which is x, to the fourth power, all over 4 factorial. Now we have to find z so that this will be the most conservative, so we can maximize this error. And this is where it actually gets confusing. This is where sometimes it's hard to follow what the authors did here. So we're going to go through it. But essentially what happened is when you're determining an approximation for a value, it's usually because you don't have a calculator or a tool to help you find the value. So if you didn't have a calculator, most people would probably not be able to find sine of 0.1. I mean, unless you're like a super genius, you would not be able to find sine of 0.1 off the top of your head. You would probably need a calculator. And in this case, if z is between 0 and 0.1, then you're probably going to need a calculator to solve this part too. And the whole point is to do this without a calculator. So what the authors of the book said was, if you draw out a sine graph, pi over 2 is over here, and this is 0. And you know that 0.1 is between 0 and pi over 2. And we know that from 0 to pi over 2, the sine function is increasing. It has a minimum over here and a maximum over here for this value. So what they said was, we can make an inequality. So we can take the sine of 0 times 0.1 to the fourth power over 4 factorial is less than sine of 0.1 times 0.1 to the fourth, or sine of z, 4 factorial, times sine of pi over 2 times 0.1 to the fourth power over 4 factorial. And we replace z with 0.1 because we also know from this graph that if we're looking between 0 and 0.1, this is always going to be increasing. So that means that the greatest value that z can be, the value for z that would maximize sine of z would be 0.1 itself. So we're going to use 0.1 as the maximizing z value. So I just plugged in 0.1 in there. So this is what we've written out here. So this is showing us that we can't actually solve for sine of 0.1 because we don't have a calculator, but we know it's between sine of 0 and sine of pi over 2. So we're making this inequality, basically. And so if you solve this out, sine of 0 is 0, so this whole thing becomes 0. And you can just rewrite this. And then sine of pi over 2 is 1, so it's just 0.1 to the 4th power over 4 factorial. And that is this step. That is this step right here. This 0 comes from here. And then this is the error that they define as the error. Sine of z over 4 factorial times 0.1 to the 4th is equal to the error of the 3rd degree, which is less than the sine of pi over 2 times 0.1 to the 4th power over 4 factorial. This is exactly this step. And then they approximate this to be, equal 0.000004. And so they just say that the error of the 3rd degree term is somewhere in between 0 and 0.000004, because we don't have a calculator, so we know that it's in between these two terms. And so then what they did was they found the range of our error by adding our approximation to both sides. So if you add our approximation to the whole inequality to all sides, then you get this, because 0 plus our approximation, 0.099833, is 0.099833. It's greater than or is less than sine of 0.1, because we know that the error plus the actual error plus our approximation will give us sine of 0.1, because sine of 0.1 minus, because our sine of 0.1 minus our approximation is our error, so our error plus our approximation will give us sine of 0.1. And then we add this value over here, 0.099833, to 0.000004, which gives us this. And that is how they got this inequality here. And that is how you would solve an approximation when you have to use a calculator but you don't have one.